Okay, welcome to class. Let me get this out of the way again. So today we are going to take more or less a meta view on PDAs. So last time we got to know what they are, how they work, and we basically just used a standard PDA. So we are going to be extending our horizons a little bit and see what other variations of PDAs are. And then we're going to work on the equivalency of PDAs and context-free languages. And I think, let me check. We kind of made already a bold statement before in the last class where we said, okay, you know, we are one layer out. So we leave the realm of everything regular. And we talked about context-free grammars, and this is on the generator side. So what is actually there on the acceptor side? And we hypothesize that this is very likely what's going to be the PDAs, okay? And then we dived into the PDAs, and what we want to do today is to actually show the equivalence between context-free grammars and PDAs. Actually, we only show it in one direction because the other direction is too complicated. And whenever things get too complicated, we just leave them. Okay, like in real life. All righty. So the first part is about those variations of the PDAs. And the second part is touching on the equivalency of PDAs and CFGs, context-free grammars. And then we're done. Oh, limitations. Yeah, what are the limitations of context-free languages? This is going to be leading over into a topic area that you will love because it's another pumping lemma. And this is the pumping lemma for context-free languages. And those considerations that we're going to make here are going to lead over into that topic area, which we are going to cover the next time. Okay. Okay, so what are variations of PDAs? So one variation is an atomic PDA, where the different things that a PDA is doing are being taken apart. So you know by now that a PDA works by doing three things. When a new state transition is being taken, it reads the input symbol, it pops something off the stack, and hey, Alex, and then it pushes a new symbol onto the stack. Okay, so this is being done all in one go. So if you have an atomic PDA, it's not a PDA that you're going to use in a nuclear power plant. It's a PDA that is taking apart these different individual actions, okay? So it's easy to see here the connection between a regular standard PDA and an atomic PDA. An atomic PDA would first read a symbol, then take a state transition to a new state, then it would pop a symbol off the stack, it would again transition into a new state, and then it would push. So how would you express the atomic PDA by way of a standard PDA? Well, what actually comes in handy is what we discussed relatively early here when we looked into this. What comes in handy is to look at these transitions where you don't eat an input symbol, where you don't pop something off the stack, where you don't push anything on the stack, or you just don't anything. Actually, we don't need that one. But convince yourself that that these lambda state transitions or partial lambda state transitions come in handy now. And specifically, when in an atomic PDA, so you just do the read and you transition to a new state. How can you express that in a normal standard PDA? Well, you have something like A and lambda, right? So, and then you are in the stage of your atomic PDA where you want to pop a symbol. Well, what you do is you don't eat an input symbol, then you pop maybe A and you don't push anything. And that leads you to a new state. And then you have yet another state transition where you don't eat an input symbol, you don't pop anything, and you push something on the stack. Okay. So what normally would have been a state transition that you take on a baby A in the input, a cap A on the stack, and you push a B onto the stack, this one piece of information, convince yourself that this is pretty much the same thing as if you would be doing this, okay? So when you go from here to here, what you actually did is you transferred or you're converted your general standard PDA into an atomic PDA. So if you do that with any of the state transitions, what the result is, you have an atomic PDA. How does that help us? Not at all. We present it here for the sake of completeness. It's more or less of theoretical value, maybe research. So we don't really care. I just wanted to expose you to that concept because it involves some critical thinking. So what I just presented, to make out of that one state, to make not state, pieces of information, 3 out of those, this is kind of critical thinking, how to do that and understand why that is, why those 3 states look the way how they look, what they are. Okay, good. So otherwise, you won't miss out anything if you forget immediately again what an atomic PDA is. It's not going to be on the second midterm. It's not going to be on the final. So, all righty. What is of interest, a little bit more of interest, is the extended PDA. So have we already used an extended PDA? What do you think? Who's for yes? Right. Very good. Yes, we have. So we had some examples. In the very last example, what is the extended part here that you should probably see? Yeah, Alex? Double, yeah, like here and here, right? And here and here. Exactly. So as you can see, this is a deviation, right, of the standard PDA, what we normally do, where you only push one symbol, one stack symbol onto the stack. So here we have 2. Is that necessary or a convenience? What do you think? Who's for necessary? Who thinks it's a convenience? Very good. It's a convenience, exactly. So how can you, for instance, make this work on a standard PDA? How can you do that? How can you transfer this into what's going to be two-state transitions, not just one? How can we make that change? So what would the standard PDA do in order to make this what you see there happen? So obviously we have an A. There's nothing wrong with that. We have the stack symbol here. So what do we push first? The A, right? I wonder, balance creates. The question is what's the bottom? So the way how we have written it here is we would do this first, and then next, what is the next symbol that we are going to eat? Obviously, we have eaten an A. Are we supposed to eat another symbol? Obviously not, right? Good. So are we going to pop anything off the stack? Are we? Who's for yes? Who's for no? Yep. Very good. So, and then we are going to have an A here. Okay. So you see what we do is we take the information for what seems to be a little bit more of a complex state transition. We take that apart. Okay. And we can easily represent that with individualized pieces of information. Right. Very good. Okay. So last question on this extended thing. Do you think we can have something like that? How about that extension? So you look at the stack and you see ABC. What is wrong with that sentence? Yeah? Yes, very good. Very good. You can only see the top of the stack. Okay. So you cannot magically look down the stack. So this is by way of how a stack works. This is out of the question. Okay. So you cannot do something like that. All righty. So the third variation is the variations in how a PDA is accepting. How does the machine accept? So remember, in the last class, we said acceptance is when? What were the ingredients? What do you think? Anything? Yeah?
Empty stack.
Empty stack, right? Empty stack. What else? What do you think? What can you say about the input string?
Is it empty?
It should have been eaten up. Right. Empty stack, empty input string. What else? Third ingredient. Final state. We also need to be in the final state. Okay. So our very straightforward standard PDA has to have these ingredients in order to accept empty input string, empty stack, and final state. Okay. So, however, depending on your preferences, preferences for intellectual challenges or whatever, you may, I mean, there's no question, you cannot give up the string empty. So in order to be able to accept the string, you need to fully consume it. There's no question about that, okay? But you can kind of dilute the other requirements. So one variation is that you accept by final state only. Final state only means that we don't care about the stack. Indeed, you may consider the machine to be kaputt. You know what kaputt is, right? Nice German word for broken. Yeah. You may consider that machine to be broken. It is incapable of recognizing the empty stack, okay? So the stack sensor, for some reason, is broken. So how can we come up with a standard machine that mimics this behavior? How can we come up with this standard machine that mimics that behavior? Yes.
Read all the characters off the stack.
We say it again.
Pop all the characters off.
We pop all the characters off the stack, exactly. And the way how we know that we did is we go by the empty stack symbol. So we put an empty stack symbol at the bottom of the stack when we start in our very first state transition. And then in this guy, in this machine, sitting somewhere in an acceptance state, what we do is we lambda from that state. And in that state, it may be, or it should be final state, right? What we do is we lambda into a final state of our standard PDA, and we pop the bottom symbol, the stack bottom symbol, and we take away the final state here of that broken machine, okay? So that way we make sure that we empty the stack. We can only reach that state, that final state, if the stack is empty without explicitly checking for the stack to be empty, okay? So which is kind of cool. All righty, so accepts by stack empty only. I leave that to your intellectual, as an intellectual challenge, you know, if you don't know what to do with yourself. So solve this problem on your own. And I don't want to discuss it here, I think, because it's on the homework. Alex?
If we make a diagram of a PDA rule that's like checking for final states that you just drew up, would that be assumed to be on there or just draw it there every time?
Well, normally we go with our standard convention.
Okay.
So we make that little bit of an exploration to see alternatives to what we have discussed so far.
Okay.
So for our purposes, we are going to go with the standards PDA, period. So that's easy enough. Okay, cool. So what you saw, and the same is true for the one that we do not discuss here. What you saw is that probably by construction, you can see, because we constructed the standard PDA, that all of these variations actually do have the same power, okay? So none of them is more powerful than another. So that's the punchline here, that we don't really gain anything by going with one of the other variations. The only reason is why we want to do it is probably the extended PDA. I encourage you to actually make use of that when it comes to the midterm and the final, because the convenience is really cool, okay? The convenience to push several symbols onto the stack makes things easier, okay? All righty. So equivalence, we speculated that probably, PDAs are on the acceptor side, opposite to the generator side. I mean, when you think about it, why did nature come up with something like that PDAs would like only partially, be in here? Why not that? Okay. So we are going to see, at least from one direction, that this is actually not true. Okay. So far we know how context-free languages can be represented, what they are. How can you prove that a language is context-free? What do? You come up with what? A context-free grammar, right? So remember, how do you prove that a language is a regular language? You come up with a machine that is accepting that, or a regular grammar, okay? How do you prove that it is not? Pumping level, right? So here, the same spiel, the same thing. So a language is context-free if we can come up with the context-free grammar. And soon enough, we can come up with a PDA. And that way we can show that a language is a context-free language. How do we prove that language is not context-free? Well, we get to know a new pumping level for doing that, okay? So it's interesting when you think about it. I mean, any language that is not a regular language could be a context-free language or above that. How do you filter that out? With a pumping lemma, right? But it's rather a rough filter, right? It throws out everything that is not regular. So now we are going to get to know next class a pumping lemma that proves that the language is not context-free, which is more specific, right? Okay, so yeah, let's get back to that equivalencies thing. And remember, we have done that several times. We have shown equivalencies by coming up with something by construction, okay? And here we are going to do the same thing. So we show by construction that context-free grammars have the same expressive power as PDAs, okay? So if we do it by construction, obviously we need to come up with a PDA that has the same power as a context-free grammar. And by construction means that once we have that PDA, we have shown that direction of equivalency. So ultimately, normally we would need to show equivalency, and that can be done, or it got to be done normally in two directions. So smaller equal to and bigger equal to, if both is true, the conclusion is it can only be equal, okay? So, however, we're going to show just that one direction and are going to be content with it. The other direction is too complicated and very technical and not very interesting either, so we're not going to do that, okay? So remember, PDAs consume strings in a systematic way. So left to right, symbol after symbol is being consumed. If we want to have a chance to actually do the same thing in terms of grammars, we should have a grammar that is producing a string systematically from left to right. Okay. So fortunately, we have exactly that kind of grammar. It's a specific form, a normal form, and the form is a Greibach normal form. So in this context, it's important here to remember ourselves that any context-free grammar can be put into Chomsky normal form, and from there you can go into Greibach normal form. Okay, so this is not a limitation in generality. Any context-free grammar can be represented by a Greibach normal form. The only disadvantage of that being that you possibly have a whole bunch of more rules, okay? But what you gain is you gain the efficiency of how to construct strings from left to right systematically. With each rule application, you add exactly one terminal. So, and this is exactly what we need here. So there seems to be an inherent advantage of the Greibach normal form that makes it lend itself very well to construct a PDA that is doing the same thing. So when you think about anything being in a Greibach normal form, so you may go directly to something that is easy. You know, that is the most simplistic rule that you have or may have, but you may have something like this. You know, remember the rule that deviated from what Chomsky normal form looks like was this. You have a terminal on the left and one or more variables following that. So what does it mean if you see that in a light that is like geared towards PDAs? We see that we produce a symbol, and the next symbol to be produced is if we resolve the C. And we know by way of the form, the shape of the grammar, whatever we replace C with is going to produce exactly one more symbol. So, and it may add actually more variables, okay? So what you see here is that we go, when we get from sentential form to sentential form, we go from left to right to solving these, applying these rules for these variables, and these variables represent work that still needs to be done. Okay, and each time we resolve the leftmost variable, we add another terminal and potentially on the right-hand side of the C, for instance here, more variables. So we need to keep track of the work to be done that is represented by these variables. So why not just put them on the stack? I mean, the direction already implies, you know, that this would be the top of the stack, and this would be, you know, one below it, and this two below it, and so on, right? And then if we pop a symbol off the stack, we eat away another symbol on the input string. So on the grammar side, we produce these terminal strings, these terminal symbols, And on the machine side, we just do the opposite. We keep eating them away, okay? Alrighty, so what does that look like? Here is an example of a grammar for a problem that we already know, a to the I, b to the I. Our favorite toy problem, which was the standard problem, you know, to show that this is a language which is not regular anymore. And we could show that with the pumping lemma. And now here we have a grammar in Greibach normal form, which is actually producing strings of that very language. So first question is, can you see that that grammar actually does produce a to the I, b to the I? So how do you convince yourself that it actually does? Just think it through for a second. So you see that the S is not recursive, as it should be. Remember, that's one of the first things that we fix, that we have a non-recursive start symbol. What does it mean? Once we leave the S, we have left it. We don't get back to it, okay? So we go from S either directly to AB, baby A, cap B, and then the only thing that we can actually do is we can replace the big B, the cap B, by a baby B. And then we have our smallest possible string A, B, if the I is bigger than 0, okay? So if we want to have more of those symbols, not just one A and one B, we get into the first rule here. And you see that this rule, B's are always only gonna go to B's, cap B's to baby B's, always. So if you want to add more to the left and to the right, you would follow this rule here. So that allows you to squeeze in as many A's and B's, A's to the left, B's to the right as you want. And it's always balanced. Okay, it's always balanced. So we know already that the B can only ever go to B. So if you keep applying this rule and you think B has already been replaced with a B, what that means is you keep putting A's to the left and B's to the right, all balanced. So the question is, finally, you need to replace that A in the middle here. Is that going to get the whole thing out of balance? Well, finally, what you need to do is you need to replace the cap A with a B. And the B goes to B, the cap B goes to baby B. So you might as well think that the A eventually needs to be replaced by baby A, baby B. So know that replacement, that final replacement of the cap A is not bringing the whole string out of balance. It actually keeps it by also adding an A and a B. So now that we have convinced ourselves that actually that this thing is actually producing A to the I, B to the I, we want to convince ourselves how the construction is being done, you know, how we construct the PDA out of the grammar and convince ourselves it's correct what we're doing. So when you take this rule here, we produce an A and we have more work to be done, which is the cap A and the cap B. So in a PDA, we do the opposite. We don't produce a symbol, we eat it away. And this is this state transition here. This first rule, we eat the A, and we don't push anything off the stack, and we add this AB onto the stack, knowing that this is the work that still needs to be done. Okay. So that step is important to understand. Okay. So if we go this rule, this here, we eat away an A, we don't produce this, we eat away an A, and we need to keep track of the work that still needs to be done, cap A, cap B, so we put it on the stack. Okay. So similarly, this one here, A is being eaten away, we put B on the stack. This is what we do here. All righty. So all of the other rules, this is kind of crazy. All of the other rules are being put and translated here. Okay. So how do we resolve that work to be done? Well, look at this rule. The work here is the B. Okay. Where does that B appear? We pop it. We replace the B in the grammar with the baby B. On the stack, we acknowledge we have that piece work that we just are about doing. We pop the B and we eat away the baby B symbol. This is what that means here. This is the equivalence of that. Okay. So you see that for all of the other rules, you know, if we have any of these rules here, any of these two rules, it means that we resolve that A, that piece of work, we pop it off the stack. Here also we pop it off the stack. And then we create new work. We push the AB onto the stack, and here the B is being put onto the stack. And at the same time, we eat away the baby A. Okay. So convince yourself that in the Greibach normal form, that range of variables to the right of a terminal, this is what we put on the stack. Okay. If we are about to do a piece of work, when we see those symbols, then we pop them off the stack. And whenever there's a variable, we don't generate it, we eat it away. Okay. So in a way, these PDFs that result from a direct translation of the Greibach normal form, they basically look the same way. That first transition that is being done is for the start symbol. So because it's a start symbol, in the beginning, we don't pop an S here. That's the reason why we have a lambda here. Okay, that may be a little bit of a confusion. You can resolve that confusion and actually pop an S if you introduce an S prime and just lambda from the S prime into a next state, and then you can actually pop an S. So here in this case, I didn't do that. It seems to be contrived. So yeah, and then you have that final state that has all of these rules. Oops, sorry. Here, okay. We have 1, 2, 3 rules here. We have 3 rules here. And if we would have 1,000 more, we would have 1,000 more here. Kendall?
So to determine like an end node, would it be any, would you just look for any of the
What do you mean by end
or
node?
the end state? The,
Oh, the final state.
yeah, the final state.
Yeah.
Would you look for where you have like the single B and then all the others that have, well,
Well, you know, in principle, anything but the rules that are related to the start symbol, all of the other rules are all in the final state
okay, would it be like that for all
for all.
created?
If we have 1,000 more rules, we would have much more here.
Okay,
Okay.
so there'll always be two states, a start and then.
Yeah.
Okay,
Exactly. Yeah. So you may wonder, well, how does that work? Well, we are on the final state anyways. What we need to be concerned about only now from here on is to eat away the input string and to eat away the stack. Okay. And we only can empty the stack once we have worked through all of the symbols, you know, like here. And if there were more, we would have much more on the stack, right? And eventually we can only halt the machine successfully if we have emptied the stack. So on the grammar side, that means if we have resolved all of the variables until we only have terminals, okay? Here on the machine side, we have eaten away all of the symbols on the stack and have eaten away all of the input symbols. So it's confusing, but after all, this is being ambiguous. There's no ambiguity because we always have these matches. Okay, we have, you know, the input symbol and whatever's on the stack, and that potentially creates new work like here. And we keep going. All righty. So that was interesting. More generally, I came up with a schematic representation of what I just said. So this here is the grammar side. This here is the PDA side. So you see that this piece of work that we are just about to do, meaning that we pop that symbol off the stack. And when we do that work, we create more work. We push those variables onto the stack. And at the same time, here we create a symbol, but on the machine side, we eat away that symbol. Okay? So there you have it. That's the direct equivalence of these two sides. Okay? And pretty straightforward to figure out why that is. All righty, any questions, you guys? Any questions? Any questions? All righty. So let's get now into our final part, last part, third part, the limitations of context-free languages. So before we had regular languages, we showed that some languages are not regular languages by using the pumping lemma. If we try to show that they are, we needed to come up with a regular expression or something regular, okay? So context-free languages seem to be pretty general, but you can already see we ran into limitations. After all, we have a stack. And the stack is a cool thing. It enforces a sequence you know, you can only see the top of the stack. And by way of using the stack, we could actually recognize languages like A to the I, B to the I. At the same time, we already realized in situations where we actually would have rather looked at the bottom of the stack first, we couldn't do that. So a string WW, for instance, is hard to recognize because we cannot look at the bottom of the stack. So with this idea in mind, you can already develop somewhat of a gut feeling whether a language can actually be recognized by a PDA or not. So grammars are elusive. We said it's pretty hard to actually see from a grammar, you know, whether it produces something that is not context-free. Well, let me take that back. That's not true. You only need to look at the right-hand side. But anyways, just looking at the language description gives you already an idea about whether it's a context-free language or not. So here, for instance, this language, we didn't do much. We just add C to the I. But you see that knowing how a PDA works, a whole bunch of marker symbols for the A's onto the stack, when we read off the B's, we would eat away those symbols again to see whether we have a match or not. And let's assume that we have a match. So the number of A's may be the same as the B's. The stack is empty. Now what? The knowledge now has been lost to check for the C to the I, whether the I is the same as the number of A's and B's have been before. So that knowledge has gone. Oh, sorry, let me mute that. 1 second. All righty, so different example. A to the I, B to the I, C to the J, D to the J. Here you can convince yourself that this works quite well. Why is that? Because the I and the J's, they are or can be looked at independently. So now you can match the A's against the B's, and then you can match the C's against the D's, and you're good. Okay. And a slight variation of that very same problem, this one down here, and we just swapped the J and the I in the middle. And now again, you cannot do it. So you see that overlap of the A and the C and the B and the D's, right? So we need to put symbols on the stack for the A's. Then we put a different symbol on the stack for the B's. Now we get into the C's. Well, darn it. We would need to reach further down into the stack to get to the symbols that were related to the baby A's, and we can't. So we cannot recognize this language by way of a PDA. Okay. So you see, whenever you have this kind of overlap, then you have a language that cannot be recognized by a PDA. What you can also see here is it would be pretty helpful if you had a second stack. Okay, because what you could do actually is, like in this situation down here, once you get to the C's, you could push over all of the marker symbols for the B onto the second stack. And that way freeing actually the symbols that you put there before for the baby A's. So, and then you're good. Okay. So you could use the second stack for the J's to save the J's. And then when the D's come, you can match the D's with those symbols and you're good. But we don't have the second stack. All righty. So how do we prove that in the general case? And this is a job that we need to do the next time. We need to get into the pumping lemma for context-free languages. And here in the general case, we can show that languages like the ones, you know, where you have the red brackets here, that those cannot be recognized by a PDA or represented by a context-free grammar. Okay. Any questions, you guys? Any questions? No questions. Cool. Let's call it a day. Happy winter again.